All right. So when we left off in our last video, here's where we were at, okay? We know what the solution is going to look like. We have the equation that we're trying to solve, and really it just comes down to how do we solve this? So what I'm going to do is I'm going to go ahead and rewrite all of this in a nicer format, okay? Shoop. Shoopity 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 shoop. Shoop. What I'm going to do is I'm going to say, I know my solution has two pieces to it. It has a homogeneous solution, which I'm going to call the complementary solution. Don't ask me why we use so many of these. Okay? It stands for complementary. It again still stands for the transient solution, okay? Yay! And then we have the particular solution, okay? And the particular solution is a steady state. All right, so I know my final solution is going to consist of two pieces. Complementary solution, key pieces of this plus its own derivative has to be equal to 0. And then my particular solution, which this has the same time function as the end solution. So, nice. Swiggity sweet. No, okay. So we got these two pieces, okay? And there are two different ways we have to solve this, okay? Because these are two different time functions, we can plug both of them back into the original equation to solve. Now, the way that our transient solution, it does require us to look at it as if it eventually goes to 0. So what we do is we take our function that we're solving, I still haven't figured out the term for it, the great day, and we just take the forcing function and make it equal to 0, and we just rewrite the entire equation. Okay, so this is that, it's just, this is 0 instead of a forcing function. Okay, and then we go ahead and solve this, because we know that this has to be true. Okay, all right. This sounds very easy. Let's do this. Okay, so that's nice. What do we do? Well, we go back to what we know. We know that C1 e to the C2t, the derivative of that is C1 C2 e to the C2t. Okay, we know that this is this type of equation. So what we're going to do is we're going to say, okay, my VCC, we're going to say it's equal to C1 e to the ST, okay, where S is C2 here. All right, that's great. And our VCP, we know that this has to have the same time function as our forcing function. Our forcing function here, we're going to assume is a DC constant voltage source. So here, VCP, because it's a DC constant voltage source, we're just going to call it C2. All right. So this is our solution, VCC plus VCP. VCC being C1 e to the ST, VCP being C2, which I guess I should have written over here, where I, was originally writing it. Okay, so what we'll do is we'll solve for VCC first. So here, this is where I had the equation that I just wrote out. CR dVC dt is equal to VC. And here, because we're solving the homogeneous, this will specifically be VCC, okay? You're gonna be hearing VCC and VCP a whole lot this class. So here, what is the derivative of VCC? Well, it is C1s e to the st. So here 0 is equal to CR times C1s e to the st. Oh, that's not an equals, that's a plus. Plus C1 e to the st. Okay, so that's nice. Now, the beauty of this is that C1 being it's a constant, I guess in other circles, because there is that capacitor component to it, and we might have multiple capacitors, C1 is sometimes written instead as A1. I'm actually going to go back and change this. I'm going to try to teach this correctly this class. This is how yeah. Good job, Kale. So I'm just switching that so that we don't have an A and a C in the same equation. It gets less confusing. So here, this one's A1 e to the st. This is A2. A1 s e to the st plus A1 e to the st. Now, the nice piece about this is if we write it out, 0 is equal to CRS times A1 e to the st plus A1 e to the st. We can divide both sides by A1 e to the st. All right, let's do that. 0 is equal to CRS plus 1. Ooh. Okay, so the whole reason why we can divide out the original solution is because the way that we set up our transient solution is the derivative of the equation has to be equal to the equation itself, which means we're not going to be ending up with the actual equation at all. We will end up with S. A1 is gone. S is the only one that remains. S, by the way, being that variable that is multiplied by t inside of the exponential. Okay, this is always going to happen. And here what we end up with is, if we solve for s, we bring the 1 over to this side, and we divide by RC, s is going to be equal to -1 over RC. Okay, we've now solved for s. That is one of the 3 values that we need inside of the system. Okay? 1/3 of the way there. Just to go back and recap, how we found S. We solved this equation, we did this in the last class. We figured out what this equation had to be, we also talked about this in the last class. I then broke this up, and then I wrote out what is VCC and VCP. We then solved for the homogeneous equation by plugging in VCC into the original equation. And when you come out of that, it erases the original function because a function plus its derivative have to be equal to 0. And what we end up with is S. Okay, now what S ends up showing us is S, we're gonna introduce a new value here. This is called the time constant. S is equal to 1 over tau, where tau is equal to the time constant. Okay, now what's so important about the time constant? Well, if tau is larger, much greater than 1, it's just gigantic, this is going to take a long time. C1 e to the st is just going to take forever because if tau is very large, s is very small, and it's going to take a long time for the function to develop, okay? So if tau is very large, transient portion remains for a long time. Okay? If tau is very small, the transient portion is very quick. It just whoop, it takes a short amount of time for this thing to reach equilibrium. Okay, so if we want the transient portion to exist for a long time, then we want a large tau. If we want the transient portion to end rapidly so that the system reaches steady state very quickly, we want a tau to be small. Okay, time constant very small. And this is the whole reason why we like a time constant, because S is just not nearly as nice to work with. All right, also, if you go back up here, this is tau. It's a fun thing. We're going to see that again in LC circuits. It's just a fun way that first order systems are developed. You end up with a fun tau value. Okay. Now there is a rule of thumb. And here I'm going to pull up my calculator real quick. The system is assumed to reach steady state in 5 tau seconds. Okay, so 5 times the time constant is equal to how long it takes from when the transient portion starts to when the new steady state is developed. Okay, so if I do my calculations here, 5 tau, if we're looking at e to the st, or here it's e to the negative t over tau, if t is equal to 5 tau, then what we end up with is e to the negative 5. Okay, now e to the negative 5, if I just do that calculation quickly, e negative 5, this is equal to 0.00674. Basically what that means is you'll have a 0.67% error by assuming that 5 tau it reaches equilibrium. Now in reality this equation actually never reaches equilibrium. E to the negative t does not at any point ever equal 0, which is unfortunate. In reality, the transient portion does equal out in about this much. 0.67% error. Oftentimes you're having that much variation in voltage system anyways. So what'll happen is you'll have a weird change in DC voltage, and what's going to happen is it's going to bump it up that 0.67% and it's going to force it to steady state, even though theoretically it shouldn't have reached it there. Okay, so comfortably we can say after 5 tau time, after t is equal to 5 tau, it is at steady state. We can make that assumption. Yes, there is a small amount of error theoretically. No, realistically, there is no small amount of error. In a real system, 5 tau, that's what it takes. Okay? We don't have perfect voltage sources. We don't have perfect components. It's going to come to a steady state in 5 tau time. Okay, so that's a fun piece. Yes, you need to know this for my class. Yes, you do. You need to understand what this means. You need to know what that is. Why does it take 5 tau to reach steady state? Well, it's because of the 0.67% error. Okay. All right. And I'm going to delete this. We have our S equation here. And in fact, I'm just going to write it as tau from now on. We know tau is equal to RC. Okay? Bam. Done. Now I can erase this portion. So I've solved one of our 3 pieces. Now we still have 2 more. Ooh. Well, what I'm going to do is, what I did to solve S was I plugged this into the homogeneous equation. What I'm going to do this time is I'm just going to plug this into the original equation. We'll see what happens. Okay, so Vs is equal to Cr dVcp dt plus Vcp. Okay, so plugging in the particular solution into the full equation. All right, so what is the derivative of Vcp? What is the derivative of A2? Well, it's 0. This equals Cr times 0 plus A2. Well, that's gross. You end up with Vs is equal to A2. We knew this already. We've been saying this whole time. This is just the mathematical way of proving it. All right, so now we know tau is equal to RC. We know A2 is equal to Vs. We do need to solve for A1 still. How do we solve for A1? Well, the way to solve for A1 involves the third equation that we have to do now, okay? So, let's do that. Sounds like a good idea, Cal. Wow, so much knowledge. You're really dropping that knowledge. This is a hard problem. You're going to be following along for days. Okay, the last one, what we're going to do is we're going to say, all right, A1 is actually going to depend on the initial conditions. Whereas A2 is only the steady state. It doesn't matter what the initial conditions are for VCP, because remember, this is the steady state solution. It doesn't matter what the initial conditions are. That's not going to affect what the long-term behavior of the system is. The transient portion is impacted by the initial conditions. It does depend, how far does the system have to move? We solve for the tau value, which is part of S, which identifies how long does it take for the transient portion. But now we need to figure out how far is that transient portion going to occur. Bam! So what we're going to do is we're going to plug in what we know from VCC into the full equation. Okay, so here we plugged this into the homogeneous equation to solve for S. We plugged this into the full equation to solve for VCP, or really A2. And then we're going to plug this back into the original equation. But in order to do so, we have to know what the system looks like at some time t. Okay? So here, we know it at some time t. Here, that time t where we know it is 0. So, okay, let's do this. We have Vs is equal to C times R times Vc, and here we'll just use the whole Vc, dt, plus Vc, okay? Plugging in the whole thing now, going in with the whole shebang. Now I know Vc is equal to Vcc plus Vcp, so I'm just gonna go ahead and write that out. Vs is equal to Cr times the derivative dt of VCC plus VCP plus VCC plus VCP. That's kind of gross. It's already getting kind of long. Why are you doing this to me, Kale? Why do you hate me so much? I don't hate you. I love teaching you. Breaking you with knowledge. CR. Okay, now we'll take the derivative of VCC. The derivative of VCC is A1 e to the st, or I could just bring that as A1 over negative A1 over tau, plus A2, well the derivative of A2 is 0, plus A1 e to the st plus A2, okay? Now we know what A2 is, we know what S is, that's great. But now we have this equation here, and we need to solve for it at some value of t. Here we have it at t is equal to 0, so we'll go ahead and plug in t is equal to 0 into this equation because we know at t is equal to 0, Vc is equal to 0. Oh shoot, I'm doing this wrong. Ignore that. That didn't happen. My bad. You only have to use this equation twice. I'm getting a little rusty. We're going to actually just plug in the original equation, which actually is slightly easier because it doesn't involve a derivative. Vc is equal to Vcc plus Vcp. My bad. I should go back and delete that portion of the video. We'll assume that I'm starting from a clean slate. Okay, and I'll just go ahead and write this out. Vc is equal to A1 e to the negative t over tau plus A2. Okay, and here negative 1 over tau is just equal to S. So I'm just writing it in this format because it's nicer. So here we know A2, here we know tau, we know t, we know at t is equal to 0, Vc is equal to 0. So here at t is equal to 0, we have 0 is equal to A1 e to the negative t over Rc, where t is equal to 0. I'm going to go ahead and plug in 0 into t, plus Vs. Okay, so I just plugged in the value for A2, plugged in 0 for t, because that's where our initial condition says, and I plugged in Rc for tau, and the only thing we don't know in here is A1. This goes to 1. Vs then gets brought to the negative side, and A1 is equal to negative Vs. All right, So that is the solution to this problem, okay? Now I am going to work through another example very briefly, just because I have to beat this topic to death. Understanding these types of systems it's a giant pain in the butt. There is no nice way of going through this. So, okay. Well, let's look at this. We have A1 is equal to negative Vs. We have all of these components out. So what I'm going to go ahead is, I'm going to go back and write out the full equation here, which is Vc is equal to negative Vs e to the negative t over Rc plus Vs. Okay, this is the solution to our voltage across our capacitor. It's very specific to this exact system. So the question now becomes, why? What can we understand about this? Well, if we graph out this function, where this is the voltage across the capacitor and this is time, what you end up with is, we know that it starts at 0. At t equals 0, you have negative Vs plus Vs. That is the transient piece. The transient piece is forcing this piece to drop back to 0, because that's the initial condition. Okay? And as we move along with time, as t increases, this value becomes smaller and smaller. It's an exponential function. And what we have is it slowly approaches the long-term behavior, which is Vs. And this is what the graph of Vc over t looks like. Okay? We have an exponentially increasing function that is decreasing because it's slowly getting closer to it, which is great. Now we can also take a few other things here. We know that IC is equal to C dVc dt. So we can also take, now what we know about this equation, we take the derivative, multiply it by C, and plot it. IC, T. Okay, if we were to take the derivative of this equation, this one drops out. And what you end up with is Vs times, it ends up being a positive Vs over Rc times C, which ends up just being Vs over R. And that's what you have. Now, the curiosity here is the equation for IC is equal to C times the derivative d over dt of negative Vs e to the negative t over Rc plus Vs, which is equal to, the Vs drops out, C times negative Vs times negative 1 over Rc times e to the negative t over Rc plus 0. Okay, so here these c's cancel out, the negatives cancel out, and you end up with Vs over R e to the negative t over Rc. And that is equal to IC. Okay, that's the equation. We just took this, plugged it into here, solved for that. Okay? What does this mean? Well, at t equals 0, IC is equal to Vs over R. What is that? That's the current through the resistor. At t equals 0, Vs over R is equal to the current passing through the resistor, because IC is equal to IR. What that means is at t equals 0, all of the voltage in the system is going through the resistor. Right there. VR is equal to Vs over R times R, which is equal to Vs at t equals 0. Nice. Now that's what we should see, because KVL has to be true at that time. It's a fun feature. When this is originally unplugged, we know this value is equal to 0. Because this value is equal to 0, all of the voltage has to be going through the resistor. Fun fact. Okay, so we will see that. It's kind of a fun feature. Now, IC does diminish with time. What does that mean? It means that the voltage across the resistor is also decreasing with time. Because if we draw out VR T, it's equal to IC, which is equal to IR, times R. It's just a scalar of this. It has the same exact time function as this. You're going to end up with the same equation, where here, this value is Vs, and it slowly approaches 0. Okay, it's kind of a fun feature here. IC is equal to IS. Because IS has the same time function as this, what we can do is if we take Vs times IS, you can talk about the power through the source, and it's going to have the same time function. It's going to start at some value, which is Vs squared divided by R, and slowly diminish to 0. Okay, so that's kind of interesting. We can solve, once we solve VC, we can then solve the rest of the system, and we can plot out the behavior, we can look at how everything works. You'll notice that this graph plus this graph is equal to the graph of Vs versus time, which is this graph. It's kind of an interesting thing. Okay, it has to be this way. It has to. The transient portion of this graph plus the transient portion of this graph together have to nullify. It has to equal 0. We force that to happen using this initial equation up here. Okay, we made all of this happen. This isn't by accident. It's required by physics. All right, we're going to go through another example. This one will be a more challenging example. It'll be an RL circuit. That'll be in the next video. So, see you then.